Hello everyone, we'll wait for some time before starting our meeting today. This is week 9 of the DLVC and this is Subrat Kumar Swain joining you from Australia, Brisbane, Australia, and we'll be talking about GANs today. I see there is no one in the meeting, but I'll wait for some time for others to join and then we'll start our meeting. Thank you.
Hi Subrat, is there a problem?
Yeah, hi. Actually, I thought like no one joined my session. I thought, is there a session going on like today or
Yeah,
is it
it's
canceled?
going on. Maybe you can take your separate session
Yes,
because
yes.
yeah,
Yeah.
it
I'll do
counted.
that. I just thought like I just saw the
Yeah,
announcement and
yeah, even for me it's like that.
yeah.
So yeah,
Is it a
but
holiday or
take
something?
it.
I'm not sure.
I don't know. I mean, sometimes it happens. So last year also it happened. So it's okay. I mean, we have to just take the session
Okay.
so that people can follow it later.
Okay. Thank
Yeah,
you.
yeah, sure,
I'll leave
sure.
the
Thanks,
chat.
Subrat. Yeah.
Thank you.
Okay.
Okay, so start our presentation. Uh, So this is week 9 of deep learning for computer vision, and this is the topic on attention and transformers. So when we look at a RNN task, so how do we go about it? So let's say we're talking about neural machine translation. So in this neural machine translation, what we do is that we sort of take sentence and we sort of translate it to a different language. For instance, here we're inputting the English as an input, and we are uh, expecting the Hindi translation of the translation of the uh, sentence. Okay, so let's say like the sentence is India got its independence from the British, and its translation would be भारत को स्वाधीनता मिली, भारत को ब्रिटिश से स्वाधीनता मिली. And similarly, if you think about another task in hand, that is image captioning. So in image captioning, you sort of have an image, and the task is that you put a caption on the image, which will be like, let's say this is the image in the left hand side, and first it will be encoded to a context vector. So the context vector is something that give us a context of the situation. So so context vector will be like taking a vector and representing the data in a vector such that the vector means something. If you think about it, it will be like, okay, here is a vector that represents this image, and here is a vector that represents that image. So if the images are similar, the vectors should be similar. So the context vector by name is that they sort of create the kind of sort of keep in mind the context of the image while getting formed. So from the context vector, we use a decoder, and that decoder is responsible for generating this caption. And if you look at this image, there is a woman playing catch with his son. Uh, a general caption would be a woman is playing, throwing at a park, right? So so it's the way people have designed these things. So if you think about it, if you think about it, the way people have designed this is that you take an input vector and you sort of get a context vector of the input, and then you translate it to something else, or you get another representation of the same data. uh, for instance, the Hindi version of the same sentence, or the caption version of the same image. So these are the tasks generally done by the RNNs, and the challenges faced by these RNNs are there are several challenges. If you could recall, two of the challenges were discussed last class. In the last class, we discussed some of the challenges of RNNs, but in today's session, we'll see the challenges that gave rise to the model of transformation or attention. So, one challenge is that information bottleneck. So if you think about it, let's just think that there is a long text, like this, like after meeting a comrade at the last station, but one before Moscow, Denisov has had drunk a bottle of wine with him, and despite the jolting roads across the snow-covered road, did not once wake up on the way to Moscow, but lay at the bottom of the sleigh beside Rostov, who grew more and more impatient the nearer they got to Moscow. So it's sort of a excerpt from the work of Leo Tolstoy. Uh, so the way like he wrote this sentence, even I couldn't get it. Uh, but the fact is that it's very difficult to memorize facts from a very lengthy article. So let's say the article is very long, it will be very tough for the machine to memorize it, because the dependency would be longer, and it's not very easy to look at the text and find the dependency from a very long context. Okay, give me a second. The very second problem that was with this RNN models was reproducing words seen very early in the sequence. For instance, let's say the word "to reach" is equivalent to zu zu erection. So let's say "to reach" is in German is zu erreichen, So erosion. I'll go with erosion. So the complete sentence is to reach the official residency of Prime Minister Nawaz Sharif. The and the equivalent German translation would be die official Residence des Premierministers Nawaz Sharif Zuerisen. So if you look at it, the term to reach uh, is translated to Zuerisen. So so the dependency between the words in the input text and the translated text is not direct. It's not like that they are translating it directly from by word to word. It's not like that you'll write 5 words in English. The translated version of these 5 words uh, tra- will be like one to one. There will be 5 words in German, and first word correspond to the first word, and second word correspond to the second word, and so on. It's not like that. Uh, there will be like cross dependencies and the modeling long-term dependencies, which is not very straightforward. And RNNs are not very good at this, so they were not very strong in modeling a different sort of dependencies across different chain. So this gives rise to the concept of attention or the temporal data. So context vector at time t is weighted average of all the hidden states. So given a time t, the context vector is a weighted average of all the hidden states. The weight vector is the measure of the similarity or alignment of the state at time t with all the hidden states. So let's say CT. So CT is let's say CT. The CT is yeah, let's say CT. The CT is a summation of alpha Tj and Hj. So here you can see x to xt as input. Let's say x1 to xt are input, and these inputs are getting transformed. Sorry, getting these inputs are like getting to the hidden layer, and each hidden layer is now getting a weighted average um, and getting the summation. Uh, so this is the context vector. Context vector is the weighted average of all these hidden states. Uh, so the weight vector, the vector of weight, that is alpha I, alpha t as a, here it is as it is written, is a measure of similarity or alignment of the states at time t with all the hidden states. So it will be like okay, so each hidden state is connected to each one of them in the outside layers. Okay, now what we're doing is that we are sort of trying to up assign weights with respect to the importance of the weights by saying that okay, this weight is associated with this branch, and this weight is associated with this branch, and so on. So when you make a decision, let's say for like for to reach to convert to enriching zoo region, then keep the weight of the initial layers low so that it will not perform the initial. But if you keep the weights of the last layers as high, it will be getting formed higher and getting formed the last, right? Also, it also depends on the spatial data. Okay, give me a second. All right. Yesterday I was taking this session and I forgot to hit recording while doing the session. So I will record the stuff now and I will try to upload it by tonight so that you can access that uh, uh, so that you can access uh, these videos in the YouTube. I think my screen is there and I'm recording as well. So yeah. So yesterday I took the session and it doesn't matter. So give me a second, like where I'll just get back to you and we'll start the session in some minutes. Okay. So I so that how this I saw that how this uh, temporal data can use attention in their mechanism to accommodate different things. Let's just talk about the spatial data. Spatial data also offers a similar mechanism for attention. Uh, so what they do is that, so as you know that the spatial data we call them as images, right? So in the spatial data, uh, yes, in the spatial data, let's say in terms of images, the spatial data would be like uh, images where the spatial correlation matters. Okay, so so for that, let's say we're trying to come up with a objective which sort of says that okay, so the spatial data is that the spatial correlation matters. So if there is an image, we can so if there is an image, we should first pass it to the CNN. And if we pass the output of the CNN to the FC network, it will lose all its spatial correlations. So what we do is that to prevent this from happening, what we do is that we take the output from the CNN layer and pass it directly to the attention layer. So you can see that. So as you know that like if there are like n number of filters, we'll get n number of outputs at any layer in CNN. And if we put all these n layers together, we'll get a 3D image sort of thing. So in this 3D image sort of thing, we first so in this 3D image sort of thing, we first try to we first try to uh, take piece by piece. So we can take a stick like a structure which is of size 1 cross 1 cross C, where C is a channel size, and we can apply attention on top of that, and we'll get a attention score at the output. The reason behind the reason behind applying attention to this small block is that what we're trying to do is that we're trying to find the weight associated with each pixel. That is 1 cross 1, 1 cross 1 cross C. So 1 cross 1 is the first pixel, and so it will the weight will be multiplied with each pixel. So these weights are parameters. When these weights will be learned, we will get very high weights for some region of the input data, and uh, very low weights uh, for some region of the image data. The reason where we're getting very low weights are called are not attended, or you can say the network is not focusing much on that part while making a decision. So the attention is low there. When the attention is higher, we will. So if you could recall here, okay, now it's not there. It's in the next slide, I guess. Uh, okay, so yeah, I sold it from a uh, blog post, I guess. Yeah. So what they are doing is that they are giving it. They're sort of giving it a way to. They're sort of giving it a way to um, do the spatial code. They sort of. So I'll just say that distill.pub. Yeah. Here you can see. You can also play around with it. I also shared the link in the chat yesterday. If you have attended it, you must have got it. So you can see that like here is a sentence that says the agreement on the European Economic Area was signed in August 1992. So let's say we're like we're just looking at the French conversion of the same thing. Um, we can see that how each word here is related with the next word in the sentence. Similarly, it's a audio wave, and we're sort of seeing how each waveform is related to the word that is represented uh, in the output. And this thing I was telling you about. So if you take each pixel and try to learn a weight, which says that which pixels are matters and which are not, at the end of the training, you'll get some pixels very high value that says that okay, so this part of the image is being referred when this word is generated. It's a task of image captioning, and so you can see he's a woman playing frisbee with his son or a kid, and the caption is a woman is throwing a frisbee in a park, and the woman is here, and the part where the woman is holding the frisbee is getting highlighted. Second thing is that a dog is standing on a hardwood floor, and the person where the dog is getting highlighted, and uh, while generating the word dog. Okay, and similarly the stop sign. Okay, so this is the way we're sort of learning a weight, learning an attention for each pixel here. So So there are different types of attention, and different types of score is calculated corresponding to different type of attention. So here is a list of things that is that is used for uh, different alignment scores. Okay, so you can just take a look at this. So now we'll see the task of image captioning. So the image captioning is first how we do that. So everything is a part of encoder and decoder framework, where the image we are seeing here is the image we are seeing here is um, the image we are seeing here is a man wearing a hat, and we call it straw hat, and we passed this image to the CNN, and so the encoder will be CNN because it is taking an image, and we'll get a context vector. So what's a context vector? If you could recall, I discussed it yesterday as well. The context vector is a vector with context. That's a bit funny to say that, but vector with context, as I say, means that uh, this vector which preserve the context of the input. Like if you take two similar image in the input domain, there will be two similar, or I can say near by distance vectors that you will find. Uh, so here, so for this type of thing, we call it a context vector, where the vector that is generated in the input layer preserves the context of the input data. So if we put it to the fully connected layer, lose all its spatial correlation. That's why we do not pass it to a lot of Excel layers. We just pass it to, and we take the output of this Excel layer and pass it to the CNN. Pass it to LSTM or RNN layers. So what RNN layer do is that they take the input from the image, and they take the context vector that is generated by the image, and they try to predict the word based on the context vector. So the context vector that you see is a representation of the word that the image is describing, and the image as well. So it's the context vector is like kind of maintaining a way to be equivalent to all these two types of data set. So when we do that, we generate the output straw hat. So before, what we are doing is that we are just doing max of 0 and double time h times x0, which is in max of 0. This is a ReLU. Now what you're doing is that we're sort of putting an attention layer as well, so that when um, so that when uh, the prediction comes for the first layer, it should not only look at the start symbol and start generating context vector. It should also look at which part of the context vector should look before making a prediction. So like the attention map is sort of a mask that is getting learned with time. So it will learn that which word before generating which word before generating a word, which part of the image it should look. So this is like the image captioning with attention. So here's the image, it is getting passed to the CNN and getting a feature vector, and the feature vector is then passed to the uh, um, um, LSTM layer, and each LSTM layer have two inputs. So you can say here it was just the previous word. So here it was just the intermediate layer and the word start, and uh, for the second word you need the previous word and the input from the last hidden layer and getting the second word. But now you can see along with the previous word A1, we're also trying to feed the uh, attention map as well before predicting something. So this is all about attention. So attention mechanism started from the paper. Attention is all you need, and they give rise to the transformers. And we'll discuss transformer in a bit. And before discussing transformer, I'll wait for one minute, like if you have any doubts or something. Oh, sorry, we're just discussing solo. Yep. Okay. So transformers. So if I've understood till attention, I think transformer would be a very easy case for. I think 6 slides are there. I can just finish it in next 10 minutes. Just bear with me. Uh, okay. So the transformer is. So give me 5-10 minutes. I'll just come back in a bit. Okay. So before so the break is over now. So before going to discuss transformers, I will also use this sorry. I'll also use a notebook to to describe about transformers because yep give me a second. Yeah. Uh, okay. So we'll be discussing about transformers now. So if you look into the slide, I'll first discuss from the slide, and we will move to the more detailed explanation, and we'll not discuss any code today because transformer is very hard to understand, and I prefer that I describe the transformer step by step and with full details. And later what we can do is that I can uh, later you can just use the there are many predefined libraries you can use, so you can use that to sort of get back at transformers or something like that, to code transformers. So starting with transformers in 2017, um, uh, in 2017, couple of scientists came up with this paper that's called "Attention is All You Need," and this paper changed the course of AI uh, in the coming days. And from transformers, it became bidirectional transformers, and now what you see, that is called Chart GPT, is also a brainchild of transformers. I mean, it's just a descendant of transformers. It's a downstream modification, or you can say future work on on this base idea. It's just an extension of this base idea. And if you understand transformers, it will be very easy for you to understand the Chart GPT working and other transformer based architectures. So transformer starts with this one. First, there is self-attention. Sorry. And after self-attention, then there is multi-head attention, and there is positional encoding and the encoder-decoder architecture. So uh, if you see there's a flow chart of the input and output prediction in the transformer, and there is a entire transformer architecture that is written in the right side. But it will be it will be better if I just take each part of the transformer and describe it to you step by step, so that you sort of have a very clear understanding of the transformer. And yeah, so first, starting with the inputs. So the inputs to a transformer, since it was a text-based paper, it would be text. Okay, and text can be changed to embedding. So let's just start with this one. Let's just start with the live notes. Okay, so let's say let's say the text is I am a good football player, comma, and I scored 20 goals in my life. Okay, let's say this is a sentence, and this part is given, and this part we have to predict. This part we have to predict. Okay, this part is given and this part we have to predict. So let's say like I'm a good football player and I scored this one. So first layer, if you see, click carefully here, it's the input layer and we're getting input embeddings. So it's very common to ask like, what is an embedding, right? So all the neural network that you see in today's life is taking numbers into account. It's like there will be ANN or CNN. So you have to pass some numbers N1, N2, NN, right? But how can we pass word into this network? It's very difficult, right? You cannot pass word into the network. So to do that, what we do is that we find embeddings. So what are embeddings? Embeddings are a representation of word in a vector field, in a vector way. So let's say I is here. So I can be written as vector v1. Then there is can be written as vector b2 and so on. So there are a couple of questions. What is the size of the vector? Depends on the user. Whatever you want to set it, you can set it. Then what is the content of the vector? So content of the vector is a semantic representation of the word. Okay. So what is semantic representation of the word? So these vectors are learned using different methods such as bag of words or word to vec or elmo. There is SIBO as well. SIBO is a type of word to vec. Then there is elmo, embeddings learned from large language models. So these are the types. Like so let's say so these vectors are so meaningful that if you take a vector of king, sorry, then subtract the vector of man from it, then add a vector of woman on it, you'll get a vector of queen. Okay, so king minus man plus woman equals to queen. Okay, so the vector should be like that much meaningful. They should be semantically very meaningful for a human being. So if a human is trying to a human being is trying to like do some operation on it, or like it should be meaningful so that the operation will also be meaningful. So there is the embedding. So what you do is that start by one second.
Video that is pod zero of the let's understand these letters cited next to each word attached. Initially, these vectors are filled up with random numbers. Later on, during training, to capture some linguistic feature, embedding values that are dated to become closer. And let's denote these embedded sequentially in order. New order aware word embedding.
Okay. So let's say I have all these words. I'm a good football player and I scored. Let's say that let's just focus on I'm a good football player. I am a good football player, and it will each word will have an embedding vector associated with it. Okay, so say each word will have an embedding vector associated with it, so that like you get a representation for each word. Two similar words will have two similar embeddings. Okay, so you go back and say we have completed till this. We have inputs, we have extracted the input embeddings, and then comes the part of positional encoding. Okay, then comes the part of positional encoding. So now we need to worry about the positional encoding that is there. So just looking at an example of how why positional encoding is important. Let's say there is a sentence uh, that says, even though she did not win the award, she was satisfied. Okay, and let's say another sentence is that even though she did win the award, she was not satisfied. Okay, listen carefully. I'll just repeat it again. Even though she did not win the award, she was satisfied. And the second is, even though she did win the award, she was not satisfied. Okay. So here you see there are two different sentences. And if you are doing a sentiment analysis of the sentiment of this, even if you do any NLP task, the sentiment of these two sentences are completely different from each other. Okay, so even though she did not win the award, she was satisfied. Like it's a positive sentiment that she is satisfied, and the second one is she is not satisfied. She was not satisfied. That's a very negative sentiment. So what we learned from here is that not only the embedding of the word matters, along with the embedding, the position of the word also matters. Okay, so uh, um, let's say in our example, I am a good football player. It's like it's a positive sentiment. If the word is I am a football player, good. So it's like saying I'm a normal football player, right? So while doing other tasks, so while doing other NLP tasks with other NLP architectures or other sequential model architectures such as LSTM or let's say RNNs, so what we are used to do, what we were used to do is that what we used to do is that we used to pass this input sequentially. Like I'll pass the input, let's say first one, and the output of the first one will go to the second, and the first and second one's output will go to the third, and so on. So all these things were processed sequentially, one after the other. Okay, it's not like that the good will be processed first and am will be processed second. But here in transformers, we pass everything at once. All this given text will be passed at once to the transformer, and um, and and everything will be processed simultaneously. Okay, so when you simultaneously process all these things, it's very crucial to let the model know that what's the position of all these things in the what's the position of all these things in the input text, right? So you cannot just pass random text to the transformer. So you need to positional information as well. So to give this positional information along with this one, we do something called positional encoding. So you see there is called positional encoding. Okay, so what positional encoding do is that it will take all this thing and it will just add a positional encoding vector to it, and it will give us a modified embedding. Now this embedding contains the semantics of the text as well as the position of the text. Okay, so let's say there was a vector embedding 1, you concatenate or add, let's say the position information of word 1 and you get EP1, let's say, for this one. And similarly for everything else. Okay, so I'll show you how exactly you add the positional embedding information. Okay, so let's go to the next slide. In the next slide we have positional encodings. uh, we concatenate the positional encoding with the word embedding. That means we are adding the positional encoding information with the word embedding, and the size of the vector will be the same after the addition. It will not change even after the addition. So it helps maintaining the order of the words in the sequence. So let's say you were adding so let's say, like, so what's the point so of doing a positional encoding? So what you can do is that you initially start by giving position number 1 to the first word, position number 2 to the second word, and so on. But this is not a good idea, because this number will increase eventually till, let's say, 10 or 30. If the number exceeds certain predefined limits, it will be like, not good for learning, because if the one input is one is 30 or 50, then it will not give us the correct scope for learning. I would say, like, there'll be a much difference between between two values, and it will not be normalized, and it will be a uniform distribution. So it will not be a good idea to learn in that way. So second is, like, we just want to put it between 1 and 0 to 1. So one way to do is that you just take the total length of the input, and so you just take the position of your text, like n, and you multiply it with 1 upon, or you just divide it with the maximum length, the entire length of the text. But in that way, if the input to the in the sentence completion task, if the input to the transformer is different, for the same word, different positional encoding will be learned. Like, if the input is I am a football player, and the second input is I am a football, so I am a good. So first is I am a good football player. The second one is I am a good. So for the words, let's say, good, the a positional encoding in the first sentence will be half, and the positional encoding in the second sentence will be 1. So there is a clear difference between that, so you cannot do that. So to overcome all these challenges, so they come up with this way of designing the positional encoding. So what it does is that the first position is the position of the text. So if it is on the third text, if it is the fourth text, it will 1, 2, 3, 4, 5, 6, and so on. So the position for all these things, so the position value for all these things is 1, 2, 3, 4, 5, and 6. Okay, is the position value. And what about the um uh okay, person is the person value. Then there is sinusoidal, and there is divided by 10,000 and to the power 2i by d. Okay, so what is I? So let's say for this, I equals to 0, 0 here as well, and here let's say I equals to k, same. So I represent the index of the index of I represent the index of an element in the vector. The person, so let's say for I equals to k, for a second positional encoding, the value of positional encoding vector will be sine of first one, I is 2 by 10,000, 10,000, right? 10,000 to the power 2i by d. So let's say this dimension is 254 and I is, let's say, 4. Okay, so it's like 8. Let's write 2 into 4 by 256. Okay, and that is like 2 by 10,000, 8 by 256 sine, that is equals to sine of 2 by 8 4 1 by 4 point 7 5 1 by 4.75. Okay, so it's pretty straightforward that oh no, it's 4 and comes 1 16 2, so it's 42 to the power 1 by 42, and you can easily calculate this one and you'll get some value. Okay, so that will be correspond, the value will go here, v. Okay, so similarly each embeddings now, so let's say this is the original embedding e1, and you get the positional embedding. Let's denote it as p I. Okay, you get ei, then you add it to pi, you get epi. Okay, so you'll get all these things, you'll get, so that means you'll get ep1 to epn. Okay, so now you got your positional encoding. And so what they did is that they use sign for the odd numbers, even numbers, and cos for the odd numbers. There's the exciting blog there out there. You can search for that. That describes why, like, using sine and cos will do the trick. Like why using the sine and cos interchangeably will do the trick. And also, since sine and cos are sinusoidal, the value varies. The value of sine and cos varies from -1 to 1. Your personal embedding will always be between -1 to 1. Okay, and since uh, yeah, since the position since you are assigning a sign of different values, so for position 3 it will be different, for position 5 it will be different. So since you're uh, querying the sine curve at different point, all of the position embedding will be different. Okay, so, and also, like, by setting different things, you are setting the frequency of the sine wave as different. So if the frequency of sine wave is different, you'll get different values. Okay, okay, so coming to the next part, if you go on to the next part, next is the self attention. Okay, so next is the self attention. So I'll describe this self-attention in a bit. Give me a second. I'll come back in 2 minutes and I'll describe this self-attention. Okay. Okay. So starting with the self attention module. So uh,
Embedding.
I will start off by uh, showing you an example of things.
Humans are born with a lot. After decades of research, Dr. Hal Pashler, a professor of psychology at the University of California, summarized our understanding of the phenomenon in the first video that is called Zero of the Neural Network here. To answer that question, you
Yep. So let's say uh, uh, um, uh, let's say I'm like working on this one, and let's say like I tell a sentence such that drug addicts, or let's say I'm a good football player, um, or let's say I said some famous statement from a movie, and ask you to like um, uh, so she looked at her enemy and whispered in in his ear, Dracarys. It's from the web show called The Game of Thrones. But if I ask you which character from the Game of Thrones told this line. So if you are a Game of Thrones fan, if you have watched Game of Thrones, you will be just by looking at the word Dracarys, you can easily tell that this was told by the Daenerys Targaryen. Okay, but like looking at the word, only we can tell this it is told by Daenerys Targaryen. We don't even need to look at all the sentence, right? So that is called attention. So which part of the sentence or which part of the image we attend to before sort of making a prediction. So we want to make a prediction, we want to tell that okay, what is this, what is that, but before doing all these things, what sort of things we look at before predicting, like what is the most important thing that we we take into account before saying it is told by something else, someone, or before classifying anything. So that is called attention. And earlier days, attention was influenced by some other factors, such as so you look at a sentence or look at an image and attend. So you attend to certain part of the image or certain part of the sentence to accomplish some other task. So let's say you are generating caption for your image. So if let's say there is an image and you are looking at the image and generating a caption for that. Let's say there is an image of a woman playing catch with a dog. But yeah, so when generating a sentence, a woman playing catch with her dog or a dog, what part of the image do you look for? You look for the woman face, you look for the dog, and you look for the ball they're playing with and the action they're doing, like the woman is throwing or the dog is catching or something like that. But uh, uh but like uh yeah, so you do not look at other parts of the things in the image, but you use this attention to generate sentences. But in that is called attention. So, but what transformer use is called self attention. Self attention is looking at itself and figuring out which part of the input or which part of it are important and should be passed forward. Okay, so to do that, we divide the sentence. Um, uh, divide. Okay, so to do that, we first divide the sentence. So we first so let's say, so I just coming back to our notebook. We have all these embeddings, and we added personal embeddings to it, and we got all these things. Okay, if we stack all these things, okay, if we stack all these things, This is EP1, EP2 to EPN. This will combinedly form a matrix of EP. Okay, right? Right. So we have a vector, so we have a matrix that is EP. We want to do self-attention on it. That is, we want to do, we want to see which part of the sentence uh, gives importance to which other part of the sentence. Okay, so what we do is that we try by making 3 copies of EP. Okay, so here is EP, 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 and all these things are matrix. Okay, matrix. So why 3 copies? Why 3 copies? So now, if you're confused, now we are discussing this one, multi-head attention. Okay, multi-head attention, and you can see there is 3 input to this multi-head attention block. So why 3 inputs? So if I go to YouTube and type Indian Idol, let's say. So this information that I got, that I typed, is the key. This is the query, and the query is matched with a lot of keys. So in the YouTube database, there are a lot of keys. So these are the keys in our database, and when the keys are matched, the keys with the highest similarity to the query is extracted. The value of the corresponding value of the uh, key with highest similarity to the query is extracted and given to us. So this is the first video came, the second video, and third video. So this is the like key, sorry, query, key, and value. Okay. Okay, great. Okay, so we got this. So this is the query, this is the key, this is the value. So, but why all these 3 are same in this case? Because in YouTube, the query is some sentence, the keys are other, and the value is something else. But here, we sort of the query and the key are sort of the same thing, because we are looking into self-attention. We're sort of looking for things, we're sort of looking for words which are more important in the same sentence. So query, key, and value are the same, are derived from the same thing. So if you go to this slide, so what you do is that, oh, okay. So before multi-head attention, I skipped one layer, that is a linear layer. So before this one, we have a linear layer. So what linear layer does is that it just take these values and compress it to a small representation. That's it. So linear layer full. So why we need that? Because we need smaller calculation, right? That's why we compress the data to smaller values. This is the linear layer, and both these linear, all these 3 linear layers are different. Okay. So once you do that, so this is our query, this is the key, and this is the value. Okay, key, query, and value. So we have this. So now what we need to do is that we need to first we need to first, so we need to do this. We need to do this to get the Z. Okay, so we got the query, key, and value. So now we need to find Z. Okay, so how do we find G? Okay, and before going to how do we find G, let's just discuss about cosine similarity. So what's a cosine similarity? the cosine similarity of two vectors A and B is given by A dot B by magnitude of A times magnitude of B. So why it is required? Why it is required? So the cosine similarity gives us a similarity score between two vectors. If the two vectors are similar, it will give a if it will give us a score of 1. If it is highly dissimilar, it will give a score of
zero will be zero. And if you remember your high school trigonometry, cosine zero, if they point in complete
minus 1. Okay.
By
If it is
taking
dissimilar,
equation
it
like
will give
this
us
conflict
minus
in
1.
dimensions.
So this can be written as A B transpose by scaling factor. Okay. Similarly, so what we need to do is that first we need to take the query and we need to find the similarity score between the query and the key, right? So as you saw, we sort of took the key and we sort of take the query and we sort of found keys that is most similar to the query. Similarly, we took the scaling factor and we scale we sort of took the similarity factor and found the similarity between two things.
Should we let us plug those in our equation?
So for this one, the equivalent thing would be you take the query, you take the key, and you divide it by the scaling factor. Okay.
And feed the same to the key. It's thing here is according examples sections course inside they take on more meaningful values.
Okay. Okay, so this is done by passing this to a block that is called matmul, matrix multiplication. Okay, so matmul.
The highest attention of provided the score.
So then you pass it to scaling. Then you pass this to scaling. Scaling. So what you did is that scaling is equal to dividing by the root of the dimension, that is minus t, and at last you apply softmax. Okay, and that is softmax. Okay. Let me first okay, it's not moving, but let's just adjust it in there. Okay, so you got I'll got
by the dimension of the key vector. In our 3 linear layer through the original.
Okay, so you can see that you'll get sorry, I need to, yeah, so you'll get output from it would be a matrix, right? So the matrix after getting trained will give similarity score between two words. If there is two words, first it will be highest against its own word, and later if you go to the second similarity score, second highest, it will give the word which is more similar to this, or the word which is more important, right? So this is the output of query and key vector. This is the output of query and key matrix when getting multiplied and getting the similarity score. So what you have, like you have a similarity score, a matrix containing the similarity score between query and its associated key, and you have value vector. So here you get the value vector, right? Value matrix. So uh, this is value, and this is the information that contains, or the mask that contains, which part of the sentence are important. Okay, so what do you need to do? So let's just look at an image. So before identifying a person's face, what do we look at? You look at this part of the image, right? Not this other part. These parts are ignored. So how do you get that? So you can say that this image is consisting of this part plus this part. Okay, so this is this part. This part and this part. So how do you obtain this image attention? By putting this mask on the entire image, and you'll get this one. So it's like saying, if you have a mask, you just multiply it with the uh, matrix from which you want to extract the important parts, and it will give you the important parts. So that's why what we will do is that we'll multiply these two vectors, and we will get the output. So if I represent all these things in one way, it will be like, you push in a vector, a matrix, and we are getting a encoded matrix. You put in a matrix and you got an encoded matrix. And if you look here, so this part is done. So if you look here in the flowchart, you have this multi-head attention that is giving the encoded part. So since we just discussed about self-attention, but we've been talking about multi-head attention. So what is that? The thing is that what they said is that what they have said till now is that you are attending to a certain part of the text. Maybe there is some other part of the text which gives which have some other linguistic information that we cannot capture in this attention head. So what we will do, we'll create several such attention head, each attention head catering to different linguistic phenomenon or different linguistic property of the sentence. Okay, so that any property will not be missed. So starting with multi-head attention. So in the base paper, they used 8 attention heads, and they they got a pretty good output out of it.
Easier to understand the intuitive information of the thing. So you better be scared that are more important. And this filtered, they learned multiple.
So what they did is that they have learned multiple attention heads, and each attention head will learn something else. So so let's say the output of this one attention head is 7 cross 7. Similarly, so this is encoder. This is encoder matrix, and you get EM2, that is also 7 plus 7. Okay. Okay. And there is also 7 plus 7. And similarly, you learn till EM8. Okay, great. So you have now 8 matrix. So what you will do, you concatenate. So you concatenate everything. You concatenate everything. And so there is add a norm and you get a norm as well. So you also add a skip connection link from here so that you do not face any vanishing current problems, and you also preserve the input information. And after this, it is passed to a feed forward network, and just to reduce the dimension of it. So you did that, and you add and took the norm, and bam, you have your encoded input, the output of the encoder. To be honest, so if you look into decoder, it's pretty straightforward. Like if you just look into decoder, I'll just put it in the slideshow mode. If you look into decoder, it's pretty straightforward, because the heads that I have discussed here is exactly the same. Add a norm, multi-head attention, feed forward network, add a norm. Okay. The output from this add a norm is going into this multi-head attention block. So that is query and key. What about the value? So why we are not looking at the value the same way we looked in the encoder network? Why we are not considering? Why we are not considering uh, the same input as value? This is because when we are considering value, the the attention should not only look at the attention should not be only give the, I mean, which part of the sentence should be given as attention should not be only uh, the inputs that we have sent. It should also look at the output as well. So you might be wondering why we should look at output. We don't have any output, right? No, we have output. We have the output here. Where is it? We have the output here, that is 20 goals in my life, but I don't want to um, show the answer or show the output to the model at once. Okay, so let's say there is so each sentence will start with the start token and end with the end token. Okay, let's say I have uh, um, I have passed my input to the encoder, and I got the input, the latent code, and I'm now passing the latent code to this multi-head attention. Okay, so once I pass this multi-head attention, so it will, so initial output is, let's say, start. Okay, and I, let's say, like, start from here, and I forward propagated my input, this encoded input to all these things, and I got a output. Okay, let's say the output I got is let's say U, but the actual output is 20. I scored 20 goals in my life. So what we'll do is that in the next iteration we'll pass 20 here. Okay, so we'll pass 20 here, and will so in the for the first iteration the start will only be revealed, and in the second iteration 20 and start will be revealed, right? Um, that is like in the first iteration I'm looking at this and the start. In the second, I look at this start and 20. In the third iteration, I'll look at this start, 20 and goals. In the fourth, I'll come till in. In the fifth, I'll come till my. In the sixth, I'll come to end of the life. Okay, end of the sentence, that is life. So how do we do it? So if you convert 20 goals in my life, that is 1, 2, 3, 4, 5 words, you'll get a matrix. Like if you look here, it's just output embedding, positional embedding, multi-dim. So output till here, as we discussed, will be a matrix, right? Matrix containing all these EP1 to EPN or EP5 in this case, right? But how do we, how do we hide certain part of the output while training the model? How do we hide these parts while, like, how do we hide this part and let the transformer predict it and not just tell them the answers? To do that, we use something that is different from the encoder. It's called masked multi-head attention, and this is the only thing that is different in the decoder than the encoder. That is called the masked multi-head attention. Yeah, so this is the attention layer and the description. Yeah, decoder, and they haven't he haven't put the mask thing in the slide, but I'll discuss it. So the mask one is like used not to use the information in the future. So the mask one, what it says that in the iteration one, what it will do, it will reveal only this start part, and it will keep all these values to minus infinity. So what will happen if we put these things as minus infinity? You can see in the multi-head mask multi-head attention, there is a sigmoid layer. I discussed there is a softmax layer here. I discussed it in the formula like this softmax layer. So when you start computing all these things in the softmax layer, it will always zero, because minus infinity is 0, plus infinity is 1, and softmax scales every value to 0 and 1. So in that way, all these values will be converted to 0. All these values will be cancelled and converted to 0. You'll have only the start value. All these values will be 0. In the second iteration, it will reveal only two sort of rows, columns, and everything else will be 0. And only these two sort of information will be used. That is that will be start and 20. Okay, so it's like that. So in that way, we are sort of masking the output uh, and preventing it from leaking it to the input while training, leaking it to the input text. So the training will go like this. You have this you have this length sentence. Let's just pass this and get the encoding, and from this encoding and from this start token, you predict the next word. That is iteration 1. Okay, you predict the next word. The next word you predicted is not good, wrong. Let me show you the first word, the next word, that is 20. So now you have this entire sentence, I am a good football player and I scored, as well as two other words, that is start and 20. So now you have all these words now, and now you have encoding of the first, all these words, like this part is coming from the encoder, and this part is coming from the encoding from the decoder. Now given this, give me the next word. So it will give some other word, the next word. If it is correct, it is good. If it is trained correctly, it will be correct. If it's not trained correctly, it will give some random word. You took the random word, you calculate the loss, you backpropagate it. Okay, and for the next iteration, you say, okay, now reveal this good word as well. Given this word and embedding of this word, you give me the next word, which is in. So how actually it keeps a word? It sort of first starts with, so it will give a probability vector at the end layer. It will give a probability vector. Each vector will give you, so it will be it is the length will be length of corpus, and each position will give you a probability of that word on that position as the next word. So if which words probability will be highest, this will be picked up and this will be it as the next word. Okay, this is the entire idea behind transformers. I think the time has over now, and the slide too. So I haven't discussed any code in this session because it's very crucial to understand the transformer first instead of looking at the code. But you can definitely look at the code that in the GitHub folder I said. Will not be much difficult if you know how to code a sequencer network. And if you're too lazy, you can just directly use the transformer library or some library of Hugging Face or something which has transformer inbuilt in it. Okay, so so this was the idea. So let me close this session. If you have any doubt or something, you can ask me in the portal. uh, till now, bye bye, thank you. We'll meet next week in the week 10. Thank you.